Hello everyone, my name is Mirta Tripsiadou and in this video I will present my research on cylindrical dice.
So let's start with our presentation. Coins, dice and cards are used daily in games of luck to make decisions. When we throw a coin, we have 1/2 chance of landing on each side. When we pick a card in a card game, we have 1/52 chance of getting each card. And when we throw a dice, we have 1/6 chance of getting each number. But what about three-sided dice? Is it possible to create a die that has a cylindrical form and equal probability of landing on each side? So, to create the three-sided dice, we must investigate the possible changes in the geometrical characteristics. But before we do that, we must investigate the physical characteristics of the cylinder, which will be the constant parameters in our experiment. So, these include a smooth surface, a stable material density which stayed the same throughout all the points of each cylinder, and a constant density which stayed the same throughout all samples. Since this is a random experiment, some parameters must be discarded. These include the human skill, the collision surface of the dice, and the height of the toss. Assuming that these parameters are not extreme, they do not matter in this experiment. Moving on to the rest of the parameters for our experiment, these include the independent parameters, which are the ones that change throughout the experiment. This is the height to radius ratio of each cylinder, and the dependent parameter, which is the one we measure, is the relative frequency of landing on each side in each cylinder. In order to investigate the changes in the geometrical characteristics, we formed two models. This is the first theoretical model, it is the arc model, which is based on the formation of a circle around the cylinder. So, we have here arcs AB, BC, CD, and DA. So, whichever arc the vertical line that connects the center of mass to the ground, whichever arc dissects, this is the side that the cylinder will follow. So, based on this type here, we need 4 equal arcs, which means that triangle BOC in this figure will be equilateral, meaning the angle B here will be equal to 30 degrees. This is the second theoretical model that we created, which is based on the surface area of the cylinder. In a common die, all sides have the same surface area. In a common coin, the surface area of the base is significantly larger. So in analogy with the common dice, we thought that a cylinder that has an equal surface area in the cylindrical side than each one of its bases will act as a fair die. These are the hypotheses that we formed based on the arc model, which was the first theoretical model. The first states that cylinders where B equals to 30 will have an equal chance of landing on each of their 3 sides. The second states that cylinders where B is greater than 30 will have a greater chance of landing on the cylindrical side, whereas cylinders where B is less than 30 will have a greater chance of landing on one of their bases. These are the hypotheses that we formed based on the second theoretical model, which was the surface area model. So, for cylinders where the height is equal to their radius, we have an unequal probability of landing on each side. So, this is not the dice that we're looking to create. In the second hypothesis, we say that the cylinders where the height is double their radius are also unequal probabilities, so these are also not the dice that we're looking for. In the third hypothesis, we say that when the dice has a height half their radius, we get equal probability of landing on each side. So this is the dice that we're looking for in the surface area model. These are the 10 cylinders that we used for our experiment. They are 3D printed, and we marked a 1 and a 2 over each side to note on which side it falls. Their dimensions are noted in this table above. Four experiments were conducted to test the hypothesis, and 10 cylinders were used. Each cylinder was thrown from a height, and the relative frequencies were calculated after 500 trials with each cylinder. This is the first experiment that investigates what is the impact of the size of the cylinder in probability when the ratio of the measurements remains the same. For this experiment, we separated the cylinders into 3 groups, which all had the same measurements but in different sizes. So, the results showed that in the cylinders of the same group, the results were the same regardless of the size. So, the hypothesis 1 is confirmed. This is the first part of the second experiment, which tests hypothesis 1b, where the height of the cylinder is the same to the radius of the cylinder. Based on the results, we see that there is an equal probability which goes against hypothesis 1b and the probabilities that we initially calculated. This is the second part of the second experiment, which tests hypothesis 1a based on the arc model, where again the height to radius ratio is 1.155 and angle b equals 30 degrees. Based on the results, we see an equal probability which confirms hypothesis 1a, and you can also see it on the graph. experiment 3, the test hypotheses 2A and 2B based on both models in the dice where the height is double the radius and B is greater than 30. Based on the results, we show that there is a much greater probability for falling on the cylindrical side than the bases. So hypothesis 2B based on the surface area model is rejected and hypothesis 2A based on the arc model is confirmed. This is the fourth experiment which tests hypothesis 3A and 3B, where the height is half the radius and B is less than 30. So, based on the results, we see that there is a much greater probability for falling on its base than the cylindrical surface. So, hypothesis 3B based on the surface area model is rejected, and hypothesis 3A based on the arc model is confirmed. From these experiments, we showed that if the dimensions of two cylinders are proportional to each other, the size of the cylinder does not differentiate the results. We showed this in experiment 1. In experiment 2, we showed that the probability that the cylinder will fall on each of its sides is equal when B equals 30 or when the height to radius ratio is 1.155. In the third experiment, we showed that the probability of the cylinder falling on the base is much less than the probability of falling on the cylindrical surface when the angle B is greater than 30. And in experiment 4, we showed that the probability of the cylinder for falling on the base is much greater than falling on the cylindrical surface when the angle B is less than 30 and when the height is half the radius. So, the arc model hypotheses are confirmed and the surface area model hypotheses are rejected. So, again for the conclusions, theoretically, the third die is the one where height over radius is 1.155. Experimentally, there were two successful dies that had similar morphology. In the first, the ratio of h over r is 1. In the second, the ratio of h over r is 1.155. Similarly, in the first angle B is 27 degrees and in the second, the B is 30 degrees. So we can say that there is room for a slight deviation of at least 3 degrees of the geometrical characteristics of the cylinder that does not experimentally affect the results. The deviation in which the results will probably be noticed in an experiment with a much larger number of trials than ours. Finally, the answer to the original stated research question is that the dice that acts as a cylindrical die is the one where height over radius is 1.155 and angle B equals 30, and the one that confirms the arc model. Some sources of error for our experiment is the 3D printer's accuracy, the 3D printer that printed the dice, the number of trials. Even though we did 500 trials, which are much, we expected that better results with a much larger number of trials,